Yes. Okay. So, welcome to the ninth class on statistical mechanics. I am Sauravi. I'm doing my PhD here at IISc Bangalore. And this is a TA class that I'm doing as a part of my PMRF TA-ship. So in this course, till now, we have started with, so long back, we started with thermodynamics, and then we went towards understanding the different ensembles, how the ensemble theory comes up, the entire probabilistic approach that lies at the heart of statistical mechanics. And from there, we gradually went towards solving for different ensembles and trying to see how one can relate the microscopic picture to the macroscopic picture and define thermodynamic quantities like pressure, entropy, enthalpy, all those different thermodynamic potentials, and how one can get the equation of states and everything, like uh, from the microscopic picture, just by considering that there is a certain probabilistic approach to how microstates get distributed in the phase space, something like that, right? So that's something we have started with, and then gradually we moved towards. So once we completed with the classical picture, we went to the density matrix formulation, where we saw that the same thing can now be looked into in the matrix formulation, and there you can actually define quantities like the probability density function. Okay, and so like once the probability density function that you have for the classical case can be now written in terms of a matrix. And in the last class, if you remember, we saw how the different elements of this matrix can, or the density matrix can vary based on whatever eigen states or eigen bases you choose. Okay, and then there can be two major ways in which you can define a system. It can be a pure state or a mixed state, and there are certain characteristics of the density matrix that comes up whether it's a pure state or a mixed state. And from the density matrix, you can define all these quantities like what is the probability of being in a certain state, what is the probability of transiting from one state to another. Okay, and from there you can also define, like from the trace of the density matrix, you can define quantities like partition function, and then gradually build upon that to go to all the different thermodynamic variables. So this is something which we have done. Today, what we'll be doing is we are gradually going towards quantum statistics. So here, energy states will be quantized, and then the main idea is that based on what kind of particles are there in the system, the certain properties of the particles would play a role here, and we would see that based on the particles, the distribution might vary. So how the particles get distributed in the different available energy states would vary, and that would change the distribution of particles, and that in a way would affect all the other thermodynamic variables. So we would look into that aspect today, and we would see what are the different types of particles majorly that we would focus on. Would be fermions and bosons, and then you have the classical particle. And so we are gradually going towards the realm of quantum statistics now. Okay, so in today's class we'll mostly we will discuss majorly the concepts, and then gradually some of the very fundamental equations and how we or relations and how we get to those relations. And normally in assignments or in even in different exams, questions come quite like questions are quite naturally from these sections. So I mean, if you know the concepts, the questions will be quite easier to solve. So we would focus more on how the equations are derived, and like not in too details, but we would go through those things and discuss the basic concepts and see how questions can come up from those areas. Okay, and if there are any doubts, we can discuss. Okay, so first, the very idea of distinguishable and indistinguishable particles, right? So you remember when we were talking about the probabilistic approach, there was this Gibbs paradox that we discussed, and we said that you have this 1 by n factorial based on whether your particles are distinguishable or indistinguishable, right? So now, what do you mean by distinguishable? Do you think that if we have two particles and the two particles are identical, is it necessary that they are indistinguishable? So are all identical particles indistinguishable, or can they be distinguishable, right? That's an important question to ask. Okay. When we are in the classical realm, there you can have two identical particles, but you can still distinguish them based on, classical parameters. Or so suppose if you have two cars at two different locations, based on the location you can, and the two cars are identical. Okay, inherently they are indistinguishable. Okay, they're identical cars. One is at point A, another is at point B. Now based on their location you can also distinguish them. You can say that that car in point A or that car at point B, right? So they become distinguishable. They can become distinguishable even when they are identical. So in classical picture, often we deal with distinguishable systems, distinguishable particles, and then in the quantum realm, what happens is, because there's also uncertainty in the measurement, there, when particles are identical, they are normally they are indistinguishable. Okay, so this character of particles, I mean, whether they're distinguishable or indistinguishable, brings in some important points. Okay, so let us consider n distinguishable identical particles in a system of total energy E. What do I mean by that? So now the total energy of the system is E, and there are different energy levels. So in energy level 1, there is N1 particle. In energy level 2, there is N2 particle, and so on. So you can say that summation over Ni is N, that's the total number of particles. And then summation over I, Ni epsilon I, where epsilon I are the energies of the individual level. So summation over I, Ni epsilon I is equal to E. Okay, the total energy of your system. So these are the two conditions that your, distribution. So if you have n particles and you're distributing it in N1, N2, N3 like this, then the distribution should satisfy these two conditions. Summation over I, Ni should go to 1, and summation over I, Ni epsilon I should go to E. Okay, total energy. Now the question is, so what we're trying to look at is based on, so suppose here we're talking about distinguishable identical particles. Okay, so we would first see for this kind of particles how the distribution happens when you have different energy levels, and now you are distributing the particles into different energy levels. What are the different criteria that come in? What governs the distribution? Okay, and then we would shift to indistinguishable particles and see how they are different from the distinguishable ones. Okay, so now the question is, how many microstates can correspond to energy E with the specified distribution Ni? So that means suppose you have a specified distribution that there is N1 particle in state 1, N2 particle in state 2, and like that. There is a distribution, okay, which is written by this Ni within the curly braces. This denotes a certain specific distribution. Now with this specific distribution, how many microstates can correspond to the total energy E? That's the question. Okay, so now you know that you have total number of particles as n, capital N, and they can be grouped into N1, then N2, then N3 dot, right? So you can say that in a way, so you can say that how many ways can you do it? So you can do it as n factorial divided by N1 factorial, N2 factorial. Right? This comes from our basic idea of permutation combination. So, okay. So this is defined as the statistical weight factor. Okay. You write it as WNI. Now, in classical physics, there are particles where the particles of a given system, even though identical, are regarded as mutually distinguishable. Any permutation that brings about an interchange of particles in two different single particle states is recognized to have led to a new physically distinct microstate. What does this mean? So, for example, if you have fifth particle in state ui and seventh particle in state uj, and then you interchange that. So now you have seventh particle in state ui and fifth particle in state uj. These two are two different microstates. Okay. So basically you had one car at point A, another car at point B, and then the car drove and they interchanged their place. Okay. So that's a new microstate. Okay. Now car B is at point A and like car B is at point A and car A is at point B. So basically they have interchanged the place. Okay. So that's a new microstate, right? So physically that's how it works. So that means now though they are identical, inherently identical, they have become distinguishable based on their position, their location, or their velocity, so things like that, right? So now including the Gibbs factor. Why? Because the particles are identical. So there is an inherent indistinguishability still there. Okay. So you have to consider that. So according to the Gibbs factor, we know that if this is the total number of ways in which you can distribute total capital N particles into these groups of N1, N2, and then because they're all identical, you include the Gibbs factor. So you have a 1 by N factorial coming in here. So the weight factor becomes 1 by N1 factorial, N2 factorial, dot, 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 right? So this is your weight factor. So the only way one can understand the physical basis of that correction is in terms of the inherent indistinguishability of the particle, which brings in that 1 by N factorial term, the Gibbs factor. Okay. So now this is your weight factor, which talks about how you can distribute, what are the different, like the number of ways in which you can distribute capital N particles, capital N distinguishable identical particles into energy states N1, N2, like in groups of N1, N2, N3, dot, dot, right? That's this term. Okay. Now, okay, so what we are currently looking at is distinguishable and indistinguishable particles. Okay. And now the question is that what happens now if the particles are indistinguishable? Okay. So till now we discussed about distinguishable particles. Now consider the case where they're indistinguishable. What does that mean? That means now taking a particle from point A to point B or from point B to point A, this interchanging of particles do not change anything. The microstate still remains the same. Okay. So according to quantum physics, okay, the situation remains unsatisfactory even when the Gibbs correction has been incorporated. Why? Because the interchange among identical particles, even if they are in different single particle states, should not lead to a new microstate of the system. So now you're talking about the quantum regime. Okay. So that means now if you want to actually consider the particles truly indistinguishable, where interchanging of particles do not matter or numbering the particles do not matter. Okay. In that case, you have to do some modification. You cannot have the previous weight factor, right? The previous weight factor does have this idea of, so their numbering of the particles, I mean, which particle went to which state matters. Okay. But in quantum physics, that does not change anything. So in other words, all that matters in the description of a particular state of a given system is the set of numbers Ni that tells us how many particles are there in the various single particle state Ui. Okay. Which particle is in which single particle state does not matter, has no relevance. Okay. How many particles are there in a certain single particle state, that is the only important point. Okay. So that means accordingly, the microstates resulting from any permutation among N particles. So suppose you have total capital N particles, and then you have, so out of 10 particles, you have put 5 particles in box A and 5 particles in box B. So as long as this number 5 and 5 remains the same, if you keep on interchanging particles, nothing changes. Okay. So that means this is the point. So the microstates resulting from any permutation among n particles must be regarded as one and the same microstate. Okay. So for the same reason, the weight factor associated with the distribution set, okay, provided that the set is not disallowed, okay, on some other grounds, then should be identically equal to unity. Why? Because there's only one way. So if you have n1 particles and then you have grouped them, once you have grouped them and the number of particles in the different groups is not changing, all are the same. Okay. So in that case, the weight factor is unity, 1. So for the distinguishable case, you have a weight factor given by this. Okay. For an indistinguishable case, that becomes 1. Now, how would this change the properties of the system? So now, because we are looking at, quantum systems also, so we will look at we'll define the system as in terms of certain wave functions. Okay. So the question is that if you are trying to define a system by some wave function, what properties of the wave function will change based on whether your particles are distinguishable or indistinguishable? Okay. What would be the properties of the wave functions? Okay. And then we would see how these properties will affect our physical observables, right? So permutation of particles refers to permutation of variables defining the system. So you can say that now your system is defined by some wave function psi, okay? And there are all these different variables. So R1, R2, Ri, Rk, Rn, all this n terms, okay? These are the n variables that might signify, suppose, the positions of n particles. Your system comprises n particles, and then they are having certain locations given as R1, R2, Rn. Okay. So the wave function psi is a function of all these terms. Right. Now you do a permutation. So this operator is the permutation operator where you change the ith, like you interchange the position of ith and the kth particle. Okay, so you choose a pair of particles, the I and the kth particle, and you interchange their position. So what happens is now Ri becomes Rk, Rk becomes Ri. Okay. Okay. So when you use this operator, this is how your system changes. So for distinguishable particles, permutation of variables result in different microstate. Okay. While for indistinguishable particle, permutation of variables result in the same microstate. Okay. Just interchanging the position. So this and this should be equal. I mean, they should not have any equal in the sense that the microstate that you're looking at is the same. Okay. So permutation of variables do not change the microstate. So now consider the case where you have the Hamiltonian, which is invariant with respect to change of enumeration of particles. What does it mean? So you are interchanging ith particle with the kth particle. That does not change the Hamiltonian. Okay. If that is the case, then that means if you have this permutation operator and then you have the Hamiltonian, so they commute. Okay. So when we know that, so if you have two operators and then they commute, then they share their eigen functions, right? So the eigenstates of H will now also be eigenstates of P. Okay. So what it means is now if you say that you are in the energy, like you know the eigen functions and they're given as psi, then Pik psi should give you some lambda psi, where lambda is your eigenvalue, right? And Pik is nothing but you have interchanged I with K, right? Interchange the location or the individual two particles. So that means this psi now is equal to lambda into psi. Okay. Now what you do again is now you again interchange them. Okay. So you have interchanged I with K and then you have again interchanged K with I. So that means you have gone back to the same state again, right? So what it means, so you have used the operator twice. So p square of psi should be equal to psi. It should give you the same state back. And from here we know that if the eigenvalue of p operator is like lambda, then the eigenvalue of p square operator will be lambda square. So you can say that psi is equal to lambda square psi. Okay. So that is already telling you that lambda can take values of plus minus 1. Okay. So that means the two eigenvalues of your permutation operator is plus 1 or minus 1. Okay. Based on that, your wave function would be defined. So if when you use your operator and you get the eigenvalue as plus 1, that means it remains the same, then it's a symmetric wave function. You say that the wave function defining the system is symmetric. Okay. Or otherwise, if lambda becomes minus 1, okay, so it changes its sign, and then we call it as an antisymmetric wave function. Okay, so a generalization of the pair exchange operator is the permutation operator. So here it's basically not a proper complete permutation, right? It's mostly a pair exchange. So you're exchanging I with K for, like, you're choosing two particles and you're like choosing a pair, and then you're interchanging between each other, right? So that's like a pair exchange operator, and the pair exchange operator has the eigenvalues of plus minus 1. Okay, that's what we found out. So now you can generalize it further to a complete, a permutation operator P, where you have multiple numbers of such permutations possible. So you can do multiple permutations with different sets of particles. Okay, that becomes a permutation operator. So you say that now you use the permutation operator on psi and you get this function back. So here P1, P2, so you see this, right? RP1, RP2, RPN. So P1 dot 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 Pn is a permutation of the numbers 1 to n. So I mean there are individual operators for each permutation, each pair-wise exchange, and then a combination of that gives you the net permutation operator. Okay. Now, if the Hamiltonian commutes with all Pik, okay, or equivalently, if the permutation operator, that is P, if it commutes with the Hamiltonian, okay, that means the energy eigenfunctions, okay, are also eigenfunctions of your permutation operator. Okay, so the energy eigenfunctions can be constructed in such a way that they are either completely symmetric or completely antisymmetric under an exchange of two arbitrary coordinates. What does it mean? So now it means that whatever be your eigenfunction for the permutation operator, they can have two characteristics. One is they can be symmetric or they can be antisymmetric. Okay, so when it's symmetric, that means for each pairwise exchange, nothing changes, right? So this is what you got, right? When lambda is equal to 1, for each pairwise exchange operator, you get the same state back. Okay, so how many times, whatever number of times you do this exchanges, these permutations, you get the same state. Okay, so that's a symmetric wave function. While in the other case, you can also have an antisymmetric wave function where you get a -1 every time you do a exchange. So in that case, based on whether you are doing an even number of permutation or an odd number of permutation, you would get a plus, like you would get the same state back, or you will get a state, or you will get a wave function with a sign change, right? So that means two options that is possible, right? So one is the symmetric case, okay? So where you get back the same state. So here A and B are for normalizations, but basically you use the operator P on the states and you can have multiple such operators. You get back the same state. That's the symmetric wave function. Or you can have an antisymmetric wave function where you have this -1 to the power P term coming in. So if you have even permutation, you get the same state back. If you have odd permutation, you have a sign change. Okay, these are the two possibilities. So now the experimental fact is that in nature, you define in nature whatever describes nature. Okay, there are only wave functions with well-defined symmetry. Okay, so the eigenvalue lambda always has the same value for each particle species. Okay, this is there. So in other words, in nature, there exists obviously two kinds of particles. Okay, one which has symmetric wave functions, where if you keep on exchanging their positions, you get back the same state, or and they are associated with integral spins, and like they are called after Indian physicist Bose. Okay, so you call them bosons. And then there are particles which are antisymmetric, defined by antisymmetric wave functions. So they're based on how many permutations you do, either you get the same state or you get a sign change, and they are associated with half integral spins, and they're called fermions, named after Fermi. So now remember, what's important in defining the number of microstates for indistinguishable particles is how many particles are there in the various single particle states. Okay, you do not care. So when you are talking about indistinguishable particles, you do not care about the numbering or the naming of the particles. You just care how many particles are there in each state, right? And now we just got to know that in nature you have particles with well-defined symmetry. So either you have symmetric wave functions or antisymmetric wave functions. Okay, so now, can the nature of symmetry of the wave functions affect the number distribution? So that means you start with n particles and you distribute them, okay, in various single particle states. It's the number of particles in each state that's important, right? So this distribution of particle, the number distribution, does it depend on the nature of symmetry of the wave functions? Okay, so let us first consider the case where you have anti-symmetric wave functions. So that means when you change, for each pairwise exchange you get a -1. Okay, so for this case, what do you get? So when you use the operator on like psi a, you get a minus psi, okay, for one exchange. So P here signifies interchange of two particles, okay, pairwise exchange, exchanging I with K, right? So you get a minus psi, okay. Now, if there are two particles in the same state initially, okay, what I mean by that? So now here, what have you changed? You have changed Ri with Rk. You have interchanged the two. Now consider there are two Ri's, okay, two particles at exactly same location, or two particles at exactly same state. Okay, so if you have two Ri states and now you interchange between that, will that change anything? It will not change, right? When you are, so basically you had one card at point A, another card at point B, and then you interchange between the two, you say that you went to a new microstate, fine. But if you had two cards at the same location, okay, and then you interchange between the two, then nothing changes, right? So that means if there are two particles in the same state initially, interchanging them won't change the wave function, right? So in that case, what happens? In that case, P of psi a becomes psi a. Okay. So now, if you consider these two equations and consider that both are possible, okay. So one says that you get a minus sign, one says that you get the same state back. Both cannot be true at the same time, right? Simultaneously, they cannot be true. The only solution that would come up from there is that psi is 0. That means the wave function vanishes. So it's not physically making any, like there's no physical relevance to that, right? Physical meaning to that. Like you don't have a system in any system anymore to define your, like the wave function has vanished. So what is this telling you? So this hints at the fact that now, if there is a system composed of indistinguishable particles, which are characterized by antisymmetric wave function, then the particles of the system must all be in different single particle states. Okay, so two particles cannot be in exactly same state, because if they are in exactly same state, once you will get this, and then from their antisymmetric nature you would get this, and they would ultimately mean that the wave function is 0, right? So this is again the result, which is equivalent to the Pauli's exclusion principle for electrons, right? So it is telling you that if you have indistinguishable particles where the particles are defined by antisymmetric wave functions, okay, which is the case for fermions, okay. So for them, you cannot have two particles in exactly same state, okay. So for particles like when you're talking about electrons, they have a spin there. Okay, so there what happens is because of the spin, there is an added degeneracy that comes in. So you know that you have an up spin and a down spin, right? So in the same state, you can put two particles, you can put a pair, either up spin or down spin, right? So there the difference is coming with the spin as well. So there's a degeneracy that comes with the spin, okay? But you cannot have two up spin at the same state or two down spin at the same state, right? So you cannot have particles in exactly same state. Two particles in exactly same state, not possible. Okay, that's the Pauli exclusion principle. Okay, that is something which we already know about electrons, right? So for this kind of particles, your Ni, which is like how many particles are there in your epsilon I state, Ni can be either 0 or 1. Okay, it's either there or not there. You cannot have two there. Okay. Now, what happens when you have symmetric wave functions? Okay, so here what we're currently trying to do is we're trying to see that based on the different types of particles. So you can either have distinguishable particles or indistinguishable particles, and they can be defined, they can have this property of symmetry in their wave functions. Okay, so now if you start with indistinguishable particles, they can be either symmetric or antisymmetric. What do I mean by that? So symmetric means if you exchange two particles, you get back the same state. While in antisymmetric, when you exchange two particles, you get a state with a sign change. Okay. So psi, if your initial wave function is psi, it becomes minus psi. Okay. So what we saw initially is that for indistinguishable particles with antisymmetric wave function, two particles cannot be in the exactly same state. And that gave back the very idea of Pauli's exclusion principle, which says that now if you have different energy states, you are putting particles in the different energy states. And there's a limit that in one state, in a single state, you can have either one particle or no particle. Okay, you cannot have exactly same two particles in exactly same state. That's the case for particles with antisymmetric wave functions like fermions. Okay, electrons, for example. Now, for the particles that are described by symmetric wave functions. So what it means, now if you exchange the particle locations, nothing really changes. Okay, so you get the same function back. Okay, so there, what it means, so here there is no such problem, right? So here, initially there was a problem that in one case, so if I go back and just recap, so in this case, there's a problem that from the antisymmetric behavior, for each exchange, you expected a minus sign. But then if you had multiple particles at the same state, then interchanging between them should not make any difference. So that would give you the same state. So these two together was making the wave function go to 0, right? But now for a symmetric wave function, for each, pairwise interchanges, you would get the same state back. And if you have multiple particles in the same state and if you keep on exchanging between them, even there'll be no change in the wave function. So now you would always get p psi equal to psi, which is consistent, right? So there is no such problem. Okay. So no such problem arises for systems characterized by symmetric wave functions. Okay. So in particular, we have no restriction on the values of number Ni. What is Ni? The number of particles in a certain energy state Ei. Okay, so you can put whatever number of particles you have to a particular state. You don't have any restriction to that. Okay, so Ni can be 0, 1, 2, dot, dot, dot. So what we have learned so far is that for fermions, which are governed or described by antisymmetric wave functions, your Ni can be 0 or 1. And for bosons, which are governed by symmetric wave functions, your Ni goes as 0, 1, 2, whatever number. Okay. You can put all particles at the same state as well. So based on that, now if you try to answer some question, so it says that consider two different systems each with 3 identical non-interacting particles. Okay. Both have single particle states with energy epsilon naught, 3 epsilon naught, and 5 epsilon naught. One system is populated by a spin half fermion and other by bosons, which have integral spin. And then you have to, so for each case, you would get a ground state, right? Ground state energy for fermionic system and then ground state energy for bosonic system. You have to find the difference between these two ground state energies. Okay. So how to do that? So basically, you have to make use of the idea that for fermions, you can have only either no particle or only one particle for each energy state. For bosons, you can have as many number of particles in any state. Okay, there's no restriction. Important to note here is that you're talking about spin half fermions. So remember, I told you that there is a degeneracy that comes because of the spin. Okay, so if your spin is given as S, we have a 2S plus 1 degeneracy, okay, which says that, so spin is an added parameter here now. So in the same state, you can have two particles, one with spin up, another with spin down, right? So this 2 is coming from this 2S plus 1 degeneracy, okay, where S is half for your case, for the case of spin half fermions, right? So based on that, can you tell me what the answer should be? Are there any questions, so far, because like you might have joined late, but any questions or anything you can ask me, okay? Like any idea how to answer the question? Like you can also write in the chat box if you want to.
I guess in case of spin half fermions, it will be, there are 3 particles, so it will be 4 epsilon 0. And for boson, I guess it will be 3 epsilon 0. So difference is epsilon 0, epsilon naught.
Okay. So bosons, I can understand. You have 3 particles. You put it all of them in the epsilon 0 state. So you get 3 epsilon. For fermions, so for fermions, what happens? So you put, so because you have a spin up and spin down, right? So there is a degeneracy coming from the spin. So that's why you can put two particles in the epsilon 0 state, right?
Yeah.
And then the third particle goes to the 3 epsilon 0 state. Okay,
so it
now
will be together 5 it will be 2 epsilon 0, the difference. Yeah. There are 2 particles, so 2 epsilon 0. Yeah.
Exactly. Yes. So that means this is now it's okay. So energy of boson 3 epsilon. For fermions, you have 5 epsilon. So that means now the difference becomes 2 epsilon. Yes. Okay. So for this kind of questions, one needs to be careful about the degeneracy that comes due to spin. Okay, so normally you could have, like, if you don't use this, you would have epsilon plus 3 plus 5, so it becomes 9. So that's wrong. Okay, so be careful about the spin, the degeneracy that comes because of the spin. Okay, now consider 3 identical spin half fermions again, and they are distributed in 2 non-degenerate distinct energy levels. The number of ways this can be done. Okay, so you have 3 identical particles. They are spin half fermions. Okay, and there are 2 non-degenerate distinct energy levels. 2 energy levels, 3 spin half fermions. Okay, how should this be done? So the basic idea is still the same. Okay, so you cannot have exactly same state, like same particle in the same state. Okay, there can be only one. There cannot be 2.
I guess it will be in 3 ways.
Okay. How do you say that?
Okay, no. You have two non-degenerate distinct energy level. Okay, so if one or two speed. No, it will be in two ways because uh, two speed.
Okay.
Let me refresh just a minute.
Huh.
Three
Sure.
identical spin half particles in two distinct way. Plus or minus that will be two. It will be in four ways.
Okay. Okay. So 4 ways. Right. And how do you do that? You
In
basically
one
consider,
in
huh,
one energy level, you put two particles. The other one in the remaining energy level, and it can be done in two ways: spin half, plus half, and minus half spin z values. And same for the other energy state. So two for this one, two ways for the remaining one. So altogether four.
okay. So, okay. So you can basically you're saying the same thing. So you're considering that you have what are the number of possible orientations of the particle, right? First, let us look at that. So you have two energy states, and the number of degeneracy due to spin is 2s plus 1. So in each energy state, you have two possibilities, up or down, right? So that means your total number of possible ways of putting your particles is 4, okay? And your number of particles is 3, right? So that means what are the number of ways? So it's just 4c3, which is 4. I mean, why I'm telling you this is whatever you have said is correct. But then in certain questions, you can have multiple number of, this number can be large. So you can have more number of energy states, more number of particles. So in those cases, actually solving it like explicitly looking at the configurations might become tricky. So there you can use this idea. So basically, you have 3 particles, and what are the different ways in which you can put them, right? So that's the idea. Okay. So the exactly same thing as you have said. Okay. So the answer is 4. Okay. Now, so till now, what we have discussed is we have discussed about different kinds of particles, and based on whatever wave functions govern them, symmetric or antisymmetric, you have different kinds of distribution. Number distribution is different. Okay. So now consider an ideal gas in a quantum mechanical microcanonical ensemble. Okay. So what I mean by that is now we consider a gaseous system of n non-interacting indistinguishable particles. We're talking about quantum mechanical system of ideal gases. So the particles are non-interacting, they're indistinguishable. Okay. And they're in a volume of like V, and the energy given is E. So it's a microcanonical ensemble. So the net energy remains constant. Okay. Now you want to find what are the number of microstates corresponding to this particular energy state E. Okay. How do you find that? That's the question. Okay. Now, because it's a quantum mechanical system now, so you have different energy levels, okay, given as epsilon I. And then each energy level has certain degeneracy given as GI. And then you can put Ni particles in the first cell, N2 particles in the second cell, something like this, right? So these are all the states with energy epsilon 1, all the states with energy epsilon 2. And likewise, you have all these different energy states. For each such state, you have a degeneracy G1, and you put in N1 particles. Okay, again G2, N2, G3, N3. So that's how you have, suppose, like that defines the distribution of particles to the different energy levels. Okay, so each such distribution set is written as this, like is represented as this Ni within curly braces. Okay. The idea is whatever you do, whatever combination, whatever distribution you do, you get the N, you are looking at all the states that correspond to these thermodynamic variables. So the system should have total number of particle as N, the volume should be V, the energy should be E. Okay. So that means the distribution should satisfy this condition where you have summation over I Ni equal to N. Okay. And then another condition is summation over I Ni epsilon I should be capital E, which is the total energy of your system. Okay. So you want to find basically all the different, number of distinct microstates Okay, so WNI is the number of distinct microstates associated with a particular distribution set. Okay, so this distribution set governs how many particles are there in how many states. Okay, so for each such distribution set, how many ways can you do it? Okay, and then summation over all such possible distributions which correspond to energy E, okay, will be the total number of microstates that's possible, right? So here, if you have to define this term, which is the number of distinct microstates associated with a certain distribution set, you can write it as product of Wi. What is Wi? Wi talks about number of distinct microstates associated with ith cell of the spectrum. So what it means is, so one is the total number of microstates. Now for each, like for that total microstate, there can be different distribution, set of distributions that one can choose. For one chosen distribution, okay, which means that this is how the distribution is. So you have N1 in G1, N2 in G2, N3 in G3, like this is the distribution. Now, for this distribution, how many ways can you achieve this? So that would be product of how many ways you can do this into product of how many ways you can do this into this, right? So now the question comes, so what is small wi? This is number of ways in which you can achieve this distribution in a particular cell. That means if your, ith cell contains, N1 particles, okay, and there are the degeneracy level is Gi, the question is the number of distinct ways in which Ni, identical and indistinguishable particles, can be distributed among Gi levels of ith cell. Okay, that's Wi. Okay, so now if we look at, the Bose-Einstein state, right? So there, what are the possible ways? So you can put as many number of particles in as many, like in whatever state you want, right? So that means the possible ways of doing this distribution, like putting N1 particles in G1 states, would be given as N1 plus G1 minus 1 factorial by N1 factorial into G1 minus 1 factorial. So it's coming from the very idea of permutation combination, right? So now this is for a particular cell. Okay, what would be the number of ways for the entire distribution? So you have to do product over all the different cells. Okay, each cell corresponding to one energy state, energy level. Okay, so this is your number of ways associated with one distribution set. And now you can have all different kinds of distributions that give you the same energy E. Okay, so that would be your total number of microstates, right? So this is for the Bose-Einstein case, where you can have all such distributions. You can put everything in the same state, and this is how it would be defined. So now you can put this expression here, right? That would give you the total number of microstates. Now what happens for a Fermi-Dirac case, where, now you can only put either one particle or no particle, right? So for this case, no single level can accommodate more than one particle, right? So that means Ni cannot exceed Gi. Okay, so if you have Gi states for one cell, you're not looking at one particular cell, right? Cell meaning only this part, okay? So you have Gi states here. You have to put Ni particles. For Fermi-Dirac case, we know that you cannot have more than one particle in one state. That means your Ni should be smaller than Gi. Okay. So the number Wi is then given by number of ways in which Gi levels can be divided into two subgroups. Okay. One consists of Ni levels, another consists of Gi minus Ni levels. So you would have some occupied state and some unoccupied state. Okay. So that's nothing but GIC Ni, right? So W Fermi-Dirac becomes GIC Ni, which is Gi factorial by Ni factorial to Gi minus Ni factorial. Okay. So again, you have to do a product over all the possible cells. Okay. So you have a distribution for this, and then you take a product of all of that. That gives you the net number of microstates possible for this distribution. Okay. So that is given as capital W of Ni. So number of ways corresponding to this distribution set. And this is product over all these terms. Okay. So this is for the Fermi-Dirac case. Now there can also be another case, which is the Maxwell case, or which is like the distinguishable case or the classical case, right? So where the particles are distinguishable, right? So now you have distinguishable particles. What is happening? Okay. So what we saw is that for one state, when you have the Bose-Einstein case, you have this kind of distribution. So this governs your number of microstates. For the Fermi-Dirac case, it becomes this, because now you only can have one particle in one state. Okay. And then you can also look at the classical case where the particles are distinguishable. So there, what it means is that now you have total n particle. Out of them, you are distributing it in groups of n1, n2, n3. So the number of ways would be given as n factorial by n1 factorial, n2 factorial, dot, dot, dot. And then because they are all identical particles, you divide by 1 by n factorial, which is the Gibbs factor. So you get this term, okay? And now for each such configurations, okay? So once you know that you have n1 particle in G1 state, for each particle, you can be in any of the states, right? So Ni particles can be put into any of the Gi levels, okay, independent of each other, because they're all resulting in distinct states, because all are distinguishable. So that means the number of states then becomes Gi to the power Ni. So that the total ways or the complete number of ways of achieving a particular distribution set then becomes product over I, Gi to the power Ni by Ni factorial. Okay, so these are the different weight factors that you get based on what particle you are talking about. Okay, we are just looking at ideal gas in a quantum mechanical microcanonical ensemble where energy remains constant. You have different energy levels with different degeneracies, and you put in different particles. Based on what your particles are, you have different kinds of distribution. Okay, so now if you want to write an expression for entropy, we know how to write entropy, right? Once you know omega, which is the number of microstates, we know entropy is given as k ln omega, right? So you can just put in this description here. So here you can do an approximation where you say that the maximum contribution to this term comes from the term where there are maximum number of microstates. Okay, so you denote it as Ni star. Okay, so you say that the maximum contribution here comes from the logarithm of the largest term in the sum. So Ni corresponds to the most probable distribution. Okay, so it's a distribution that maximizes the number of microstates. Okay, it's the most probable value of the distributions Ni. Right, and now because there are two conditions that you have to satisfy, right? You want to find this distribution. Okay, you want to find the most probable distribution numbers, but that is associated with two conditions. One is that the number of particles should remain equal to n, total number of particle, and total energy should be E. So there you use this idea of Lagrange undetermined multipliers. So you put in all these two conditions, and then you said that delta of this term should go to 0 because you're looking at an extreme value where you are trying to maximize the number of microstates. Okay, looking for the case where you get maximum microstates. You put in the Stirling approximation, and this is what you get. Okay, so this is this ln W term that you have here. Okay, so now based on different values, okay, whatever. So here you have this term A, which talks about different kinds of particles that we were talking about. Okay, if you choose A as -1, it becomes the Bose-Einstein case. If you choose AS plus 1, it becomes the Fermi-Dirac case, and 0 corresponds to the classical case. Okay. So if you had solved individually, you would have seen that this is the general form that it takes. Okay. So now, if this is your expression of L and W, you can just put in here. Okay. And basically, you're trying to look for the case where you get the maximum number of microstates, and that would, so basically you're putting this to 0, delta of this term going to 0. Okay. So from there, this is an important relation that you get. So this tells you that Ni star turns out to be directly proportional to Gi, which corresponds to the degeneracy that is there in your system. Okay. And then you have this to the power alpha plus beta EI plus A. Okay. So A deals with the type of particles that you're talking about. Okay. If you remember our initial, previously when we had talked about the different ensemble theories, we had this mean occupation number coming in there, right? Which again meant what is the average number of particles that are there in different energy states. And there also you had a similar form with alpha and like alpha given as mu by kT and beta given as 1 by kT. Okay. So you can say that this is your most probable distribution. Now Ni star by Gi. So you're basically, excuse me. So you can basically now, look at the most probable number of particles per energy level in the ith state. So you're dividing by Gi. Okay. Okay. So it depends on what kind of particles you're dealing with, which comes in A. And alpha is given as mu by kT, beta is given as 1 by kT. So this comes, you can correlate it with the ensemble theory results that we had initially solved and see that alpha and beta is associated with the chemical potential and the temperature, things like that. Okay. So the most probable value of N, okay, in our energy level is then given by this value here. This is your expression. Okay. Now, what do we get out of it? So now you can put in that value, right? You can put in the expression of Ni star that you have just solved for and try to solve for the entropy, right? Now, once you explicitly write the expression for alpha and beta and try to simplify, you would get a term like this. And remember from our ensemble measurements as well, you had an important term like PV by KT in the grand canonical ensemble as well, like if you correlate, where this was associated with some potential, right? So basically now you are getting back a relation with thermodynamic quantities. Okay, you started with the very quantum mechanical, approach to just distributing particles in different energy levels. But now you have a relation that relates entropy with different other thermodynamic variables. Okay. Now from here one can define thermodynamic pressure of the system. So basically you can take this term to the left hand side. Okay. You can explicitly rewrite this terms. So you would get KT by A summation over I, this term here. So what it means is the expression for pressure now has a direct relation which looks at what particle we are talking about, how the distribution is, what are the degeneracy in the energy levels, right? All the information comes in here. Okay. So in grand canonical ensemble, you had PV by KT is equal to ln Z, where Z was the grand canonical partition function. Okay. So you are gradually building that analogy between the two. Okay. Now, if we now go to the canonical ensemble, okay, so you're talking about, initially you're talking about microcanonical ensemble where the energy was constant. Now you're talking about canonical ensemble. So what changes there? So now you know the expression for partition function for a canonical ensemble. So your weight factor here now becomes e to the power minus beta E, right? So this is how you define the canonical partition function. Again, your total energy should satisfy this condition. Your total number of particles should be given by this relation. Okay. So what you can do in this expression, you can put in these values, right? So you can replace total energy E by this summation. You can say that there are different energy degeneracies that are coming in the energy levels, which are given by G of NE. So this is not exactly degeneracy. This is the kind of, this deals with the number of ways in which you can achieve this distribution. Okay. So GI is the statistical weight factor, okay, associated with the different kinds of distribution. So if you have a Bose-Einstein distribution, GI becomes 1. Okay. In case of a Fermi-Dirac distribution, what happens? If your NE is the number of like particle in each state. If NE is 0 or 1, you have the weight factor going to 1. But for all other cases, it is 0 because that is not possible, right? That does not happen for Fermi-Dirac case. And then for classical case, you have the weight factor given as 1 by NE factorial. So this is something which we derived at the very start of the class today. So these are the different weight factors, which talks about what is the weightage of distributions for individual states. Okay. And this is how you write the partition function. Okay. So statistical weight factor, initially this was written as WNI. Okay. So now for this definition, you have written it as GNI. So this is not the exact degeneracy that you're talking about. This is talking about the total statistical weight factor associated with a particular distribution set. Okay. Okay. So now let us calculate the canonical partition function for the Maxwell-Boltzmann case. Okay. So that's a distinguishable particle. Okay. So we know how GNI looks like. This is the general definition of your canonical partition function. Okay. Now GMB, the Maxwell-Boltzmann case, is given as product of over epsilon 1 by n epsilon factorial. So you can put that expression here. Okay. Now this is rearranging of terms. Basically, you have a product here, so you can rearrange it and write it like this. Okay. N, you have a 1 by n fact. You can write in 1 by n factorial and put in a 1 n factorial here. So you can do all these combinations. Now, what you get out of this, okay, is important. So you say that basically you can rewrite this as, something like this. So why is it important? Because this corresponds to the canonical partition function for one particle. Okay. So now you are again getting back the same expression that you had for non-interacting particles when we started with the classical description, right? So canonical partition function for n particle is equal to canonical partition function for one particle to the power n by n factorial. So you're getting back that expression. Okay. Now, for a single particle, how do you define it? So for a single particle, you can write it as summation over epsilon e to the power minus beta epsilon. And then you can consider that the energy states are very closely spaced. So you can go to an integral. Okay. And if you do an integral, this is how it would look like. So here you're considering free particles, okay, where the energy is will be given as it will have a p square by 2m kind of dependence. So, and then from there, this is how it looks like. So this is something same as we had solved for the classical cases. So for one particle, you get V by lambda cube, where lambda is your thermal wavelength. Okay. And then for n particles, it would be to the power n by n factorial, right? So this is how you get back the same expression that we had solved for the classical case. For the grand canonical partition function, you would have an extra term, which is the fugacity, which comes like e to the power mu by kt to the power n. This term comes in because now for the grand canonical case, your number of particles is not constant. You can also exchange particles. Okay, so that's the additional term that you get. Okay, so if you have to write the partition function for a grand canonical case, that would be given as, so this is for the canonical case, and then you have z to the power n, where z is your fugacity. Okay. Now let us look at the indistinguishable cases. Okay, so now for the indistinguishable case, there are two options. One is the Bose-Einstein case, another is the Fermi-Dirac case, right? The only difference lies in what are the allowed values of Ni. Okay, weight factor is 1 for both cases, because for both cases the particles are indistinguishable. So the weight factor is 1, but because you have this difference of symmetric wave function and antisymmetric wave function, you have difference in the allowed values of Ni, and that's the only difference. Okay, so now if we have to look at this, is the general expression, right, for the grand canonical partition function. So here you can see this part corresponds to a particular value of n, and then you do a summation over all possible values of n. Okay. So these are like individually like a canonical expression. And then you say that for one particular n, this is the possible way. And then you relax the n variable to saying that your n can also vary. Okay. That's how you go from canonical to grand canonical. Now, you can rearrange the terms and write it as, so this remains. Here you have minus beta summation over G, summation over epsilon n epsilon E, right? This is your total energy. So you can rewrite it because you have a, so this is just summation in the power exponents. So you can rewrite it as something like this. Okay. So here the double summation. So you have a summation over n and then you have summation over all the different distribution sets, right? Two summations. The first over number n epsilon, okay, constrained by a fixed value of total n, and then over all possible values of n, okay. This can be equivalently written as a summation over all possible values of n epsilon, independent of each other. So initially what you have done, you have chosen one capital N, and then you have said that for that capital N, what are the different distributions possible? So this is summation over all such distributions. And then in the next step, you relax the total number of particles. You say that now n can vary. That's this two summation. But that is equivalent to again writing that now you have multiple summations over different n epsilon values, and each of these n epsilon values can take any value from 0 to infinity. Okay, they are equivalent. So now what you can do, you can have multiple summations for each values of n0, n1, n2, and each can range from 0 to infinity. Okay, that would also give you the same relaxation in the number of total number of particles as doing this summation, two summations, right? So now you can individually have all this, product terms, okay, for n0, n1, dot, dot, dot. So in the Bose-Einstein case, what happens? In the Bose-Einstein case, n epsilon, okay, so all these values that you are putting in, okay, can be 0, 1, 2, whatever. But for a Fermi-Dirac case, the individual values of n0 in like all n epsilon terms can be either 0 or 1, right? And then you can have many number of such products. There is no restriction to that. Okay. So that means now, basically, if you solve for the two cases, in one case you put all values of n epsilon going from 0 to infinity. In another case, you just have two values, 0 and 1. You would get an expression for the partition function, which has a form like this. So now for the Bose-Einstein case, this is how it looks like. For the Fermi-Dirac case, this is how it looks like. Okay. With this condition, z e to the power minus beta epsilon less than 1. So this is associated with, so it relates. Remember, z is the fugacity. So it is associated with the chemical potential. Okay. So it relates the energy states and the temperature with the potential, this condition. Okay. So once you know Q, okay, you can define this Q potential for the canonical partition, grand canonical system, which is given as PV by KT. This is same as how we had defined it for the, when we were solving for the different ensemble theories before. Okay. So you can write it as ln(q). So now you can take a logarithm of these terms. This is the term that you get. So based on whether you have a Bose-Einstein particle or a Fermi-Dirac particle, okay, the signs will change. So in a general way, if you have to write it for all the different cases together, this is how it would look like. Okay. So here -1 corresponds to Bose-Einstein case, +1 corresponds to Fermi-Dirac case, and 0 corresponds to the classical case. So now you know how PV by KT looks like. Okay. This is your Q potential. So now once you have this, you can actually get all the different thermodynamic variables starting from here. So you can get energy, like average energy, number of particles, entropy, all of that. Okay. So it's important to know how to get there and to some extent, remember this. Okay. So now if you have to define total number of particles or total, or maybe average number of particles or average energy, right? How do you define it? So this is something which we have already done when we were talking about grand canonical ensemble before. We know that if you know the potential, Q potential, which is given as PV by KT, We know this is the relation for average number of particles. This is the relation for average energy, right? So basically now that means you know the expression for Q, okay? You can do this derivatives to actually find an expression for average energy for average number of particles. Okay, this is how it looks like. Okay, and if you have to compare it with our initial, like definition, this is how it goes. So you can understand this is associated with some, distribution, some occupation number, mean occupation number, some distribution that we're talking about. And then for each such distribution, when you're talking about energy, you are multiplying it with the individual energy levels for that state. Okay, and then doing a summation over all possible states, right? Charge. Okay. So you can write this, the average energy, as summation over epsilon, this term, n epsilon, right? This here is the mean occupation number. So what is this telling you? This is the mean number of particles in the epsilon energy state. And then you are taking a summation over all possible energy state. That's how you get the total mean number of particles, right? So this is important, okay? So you define the mean occupation number as this term here. You replace Z and beta by 1 by KT. So this is how it will look like. Based on what kind of particle, your A will change. Okay. So from here, if you want to plot how your N looks like, this is how it will be for the different cases. So you can see for the fermions, okay, it never exceeds 1. Why? The mean occupation number never exceeds 1. Why? Because fermions, you can either have 0 or 1, right? Your individual n epsilon terms can be either 0 or 1. So that means when you do a mean, that is always less than 1. Okay, so this is, as you can see here. Now for the Maxwell-Boltzmann case, you can see this goes like this. While for the bosons, there's an interesting point where you see that as you go close, so as mu approaches epsilon, okay? So as you approach 0 here, this almost diverges. So it's like you are putting all particles at the same state. What is this telling you? So that means if you have a lower limit to energy, your energy states have a lower limit, and then when your mean occupation, your chemical potential is very close to this value, epsilon, okay, at that state, all particles, like the mean occupation number diverges, which means that all particles get accumulated at the lower energy state. And that's the very phenomena of Bose-Einstein condensation that we'll read in details later, but that comes up in this signature here, okay? And this is the classical case that you see. At very high temperatures, as you can see here, okay? So when temperature rises and or at very low densities also you can say, so all of this merge together, okay? So you get a similar value coming in here, okay? So this is what we have been discussing. So in the Fermi-Dirac case, the mean occupation number never exceeds unity, okay? And you can see that for epsilon less than mu, okay, when epsilon is less than mu, the mean occupation number tends to its maximum possible value of 1, as you can see here, okay? In the Bose-Einstein case, we see that there is nothing in this region. So there is nothing for the case where epsilon minus mu is less than 0, okay? So we must have mu less than all epsilon. So your chemical potential should be lower than the available lowest energy value. Okay, that's what it means. Chemical potential should be equal or lower than the available energy values. Okay, the lowest energy value. And then you can see that when it matches or as it tends towards, like this term tends towards 0, the occupancy of that particular level becomes infinitely high, which is associated with the phenomena of Bose-Einstein condensation. Okay. In the Maxwell case, where A is 0, you get a typical exponential kind of dependence. So e to the power minus epsilon by kt, which is what is expected in the classical description as well. Okay, so these are the different ways in which the mean occupation number, which talks about how the particles are getting distributed in the different energy state, changes based on what particle we're talking about. Okay, and then so now based on this value, all your expressions of average energy, average number of particles, or other thermodynamic variables would accordingly change. Okay, now here, I mean, so this is a point that, see, the important point to note here is that the distinction between quantum statistics and classical statistics. Okay, so that's a point. If I have to summarize what is written here, this fugacity which you have, like e to the power mu by kt, that governs whether we are in the thermodynamic limit or in the classical limit. Okay, so probability of any of n epsilon being greater than unity is quite negligible. Okay, with the result that classical weight factors become essentially equal to 1. The distinction between classical treatment and quantum mechanical treatment then becomes rather insignificant. Okay, so that's what is happening at this limit here. Okay, when e to the power epsilon minus mu by kt is much greater than 1, you are in this regime where there is not much change between the energy states are quite close, and you can have all, like for each states, the classical weight factors, which is like one product over 1 by n factorial, that actually goes close towards 1. Okay, which is also close to the quantum limit. So there the difference between classical and quantum goes away. Okay, it becomes negligible. The difference is quite higher at this end. Okay, so for large values of epsilon minus mu by kt, the quantum curves 1 and 2 essentially merge into the classical curve. Okay, so high temperature, okay, low density, those are the regions where it goes towards the classical limit, and that is governed by this term here, the fugacity. Okay, the fugacity of the system must be much smaller than unity. Okay, that's the case which also came up here. If you remember, if you look at this condition here, this also tells you the same fact, that when this condition holds, then we are in the quantum regime. Okay, now we know the mean occupation number. Okay, and that tells us what is the average distribution, how the average distribution of particles are happening. But now for each energy state, when you are putting n epsilon number of particles, there can be a statistical fluctuation in n epsilon. Okay, so how do you define it? So from our if you correlate it with our ensemble discussions before, this is how it goes with the partition function. Okay, this is how it's related to the partition function, the average of n epsilon. Okay, and then you can also define n epsilon squared. So basically you want to look at variance. So you are defining now the different moments, and then you would take the difference of the two and try to find the variance from there. Okay, and this is from our well-known relations that we have discussed before. So you know an expression for n epsilon average, you know an expression for average of n epsilon squared. So you can define a term like n epsilon squared by n epsilon whole square, right? Like this is your basically variance that you are defining, and from there you can also define standard deviation and all the other terms. Okay, you can take this ratio. So now if we have to summarize, this is how it looks like. So here it is telling you how how this n epsilon fluctuates based on whatever number of particles you're talking about and whatever kind of particles you're talking about. Okay, this talks about the statistical fluctuation in n epsilon. Just a thing to keep in mind. Okay, now till now we have been talking about summation, like when you described, suppose this relation, we were talking about summation because we have looked at discrete energy levels. We are talking about a quantum system. So we said that there are discrete energy levels with like epsilon are the different energy states, and this is how the summation is defined, and that's how you can find a relation between how the distribution is in different energy state to thermodynamic quantities like pressure, volume, temperature, right? This is something we derived. But now consider the case where you have a large volume and the energy states are too close, okay? They're not too separated. So there, what happens? We can go to the integration. Just rewrite it in terms of integration, okay? So if you want to rewrite this in terms of integration, this is how it would look like, okay? Basically, now you have done an integration over the phase space volume, okay? So you have written, so 4 pi p squared dp. Now, if you do integration by parts, okay, what would happen? This term would go away. What would remain is only this term, right? So what is this telling you? This is telling you that you have this d epsilon dp term. That means based on how energy is related to momentum, what is the functional form of energy related to momentum, that would be an important point here, okay? So if you have free particle, you're writing it as p squared by 2m, while for a maybe relativistic particle, you write it as p into c. So the expressions would change, and based on that, your expression for thermodynamic variables will also change. And then you have this term here, which is, see here again, this is nothing but your mean occupation number coming in, right? And A would define whether you have a fermion or a boson or a classical particle, okay? So now you can define energy as well, okay? How do you define energy? So you know that you had a summation, right? So initially, now you're going from summation to an integration in the phase space. So you write an integration over dr dp. You have a 1 by h cube term coming in because of, it's just the minimum phase space volume covered by 1 microstate, okay? This is your mean occupation number, and this is your individual energy states that are possible, and you're doing the integration over all of that, okay? So if you have to explicitly write it, this is how it would look like. So here, again, you have this term coming in, right? So E is given by this term here, and then P is given by this term here, okay? So you can define this integration that you have here as EH cube by 4 pi V, right? This is just rewriting this integration, this part, okay? So this part is written in terms of energy as EH cube by 4 pi V. This is your first relation, okay? Now we will use it in the expression for pressure, okay? So for pressure, you have this integral, okay? So you consider free particles. So you consider epsilon as p squared by 2m. So from there, you get the expression for this term, okay? So here you are again getting back the same integral that you had here, right? So you can replace this integral by h cube e by 4 pi v, okay? So this gives you now a relation between energy and pressure, okay? Thermodynamic pressure and energy and volume. So this is for non-relativistic particle. Now, if you have a relativistic particle, what will happen? This term here would vary, okay? So accordingly, you would have a variation in the expression as well, okay? So what would happen for a relativistic particle? So there you can consider that energy is given as this. So considering rest mass to be negligible, epsilon is given as P into C, okay? So now everything remains same, only this term changes, okay? So your integral now looks like this. So again, you have a similarity. So only there'll be only change in this term that you get here. So the process remains the same based on whatever system you're talking about and what's the relation between energy and momentum. Okay, what is the relation? Your this derivative would change, and accordingly your expression that relates pressure to energy will be changing. So now for a relativistic particle, you get this. And if you remember, these are same as what we have been deriving when we did for the classical case as well. Okay, so here, because when we're talking about, once you go from the from the summation to integration, you're assuming that the energy states are quite close, the volume is large, so you're actually going towards the classical description. Okay, and you are seeing that you're getting back the same results that you have initially found for the classical treatment. Okay. Now, ideal Fermi gas. Okay. What happens here? So this is your general expression. Now you want to put in So here you have replaced A with +1 because you're talking about Fermi gas. For a Bose-Einstein gas, you would replace it as -1, right? So based on whatever system you're talking about, your you have to replace the mean occupation number accordingly. Okay, other things remain the same. So this is your basic definition of the potential, like PV by KT. This is your expression for the number of particles, where this term here is your mean occupation number. So now you can go from again summation to integration, and this is how it would look like. Okay. So considering non-relativistic gas, again you do a substitution. So here what you can do is basically you can go from momentum space to energy space using this relation. Okay, just substituting, doing substitution and changing the variables, you can go from momentum space to energy space, and what you get here is a kind of a density of states, right? It tells you that this is how the density of state varies when you have a ideal Fermi gas in a three-dimensional case. It goes as epsilon to the power half. So you get this term coming up here. Okay, so this is n. Similarly, you can also find an expression for average energy. Okay, so all the terms you can define. Now here, this integral, okay, this integral that you have here, you can write it as f of nu z. Okay, so this is a well-known series, and you can rewrite your integral in terms of this term here. So now what you get n by v is equal to g by lambda cube f of 3 by 2 z. Basically, why 3 by 2? You're comparing with this exponent, okay? Comparing with the exponent that you have here, okay? And then you're rewriting this term in terms of the thermal wavelength. So this is what you end up getting. This is for a ideal Fermi gas, okay? So now you can also rewrite it as P by KT. So basically, you know how pressure, PV by KT, you know that relation. So from there, you can also define P by KT as G by lambda cube F of 5 by 2 Z. Okay. How 5 by 2? Again, look at the expression for pressure that you had initially defined. So once you know N, you can also use this relation to relate with pressure. Okay. So here G is the weight factor, which is arising due to the internal property or the structure of the particle, like spin. Okay. So if you're talking about what do I say? Electron. Okay. So then you have a spin half particle. So that would change your G. Okay. Now, what happens at low density of particles or at high temperatures? Right. So again, you're going towards the classical limit. So you can say that at low densities or at high temperatures, how do we get back the classical results, right? So you can see that when T tends to infinity or at low densities, what happens? This is your definition, right? This is how N by B goes as G by lambda cube F of 3 by 2 Z. So that means F of 3 by 2 is given as, so N by B, you can write it as small n, which is the number density. So small n lambda cube by G. Okay. So now lambda cube is nothing but your thermal wavelength. So you can write F of 3 by 2 in terms of temperature here. Okay. Now what happens when your n is lower or temperature is quite high? Okay. So you can say that this term is much, much smaller than 1. Okay. Now what does this mean? So if this number is much, much smaller than 1, you can approximately say that f of z is nothing but z. Right? So you can say that z is much, much smaller than 1. So f nu of z is approximately z. Okay. So if you substitute that here, you would again get back the results that you have got for the classical gas. Okay, again, PV equal to NKT, energy is given as 3 by 2 NKT, CV equal to 3 by 2 NK. So all the relations that we had initially derived for the classical case, you would get them back. Okay, and this again validates this point that when you are in the classical limit, all this, different distributions, they merge. Okay, so this limit basically. Okay. Okay. So now that means what we have discussed so far. So we started with, in this case, we defined this relation. So as we were going from summation to integration, we defined this relation. Okay. And from there, we derived the different thermodynamic variables and the relations between pressure and energy and volume and number of particles and all of that. And based on what type of particle you're talking about, what is the energy dispersion relation, you can actually relate these variables. So you can get, the equation of states from here. Okay. And for different particles, so currently, so here we have been discussing about, this is a general definition, right? This is the general case for any value of A. And now you can go to a particular value of A. That means you can choose either you're talking about Fermi gas or Bose gas or Maxwell-Boltzmann, like the classical case. And based on that, you can get all these different relations, right? And again, in thermodynamic limit, you get back the classical case. Okay. Now, what happens at low temperatures? Okay. Low temperature is the important, interesting point because that's where the quantum aspects are more dominant. Okay. So at low temperatures, what happens? N lambda cube by G would tend towards 0 because it tend towards infinity because lambda goes as 1 by, like it has T in the denominator, right? So this would go towards infinity. Okay. So in that case, if you look at the mean occupation number, okay, this is your mean occupation number, right? So here two cases can arise. When energy is less than mu naught, okay, you get 1. While energy is greater than mu naught, you get 0. Why? Because see, T here is now tending towards 0. So if you put, so suppose your, energy is, epsilon is less than mu naught, okay, what happens? This term is negative. Epsilon is less than mu naught. So the numerator here is, like this term here is negative. And then your T tends to 0. Okay. So you have minus of 1, or minus of, maybe consider it as 1. Okay. So minus of 1 by 0. Okay. So it's like minus infinity kind of term, right? So then this term vanishes. So what you get the mean occupation number as essentially 1. On the other case, where your energy is greater than, like epsilon is greater than mu naught, what happens? This term is a positive quantity. So consider maybe close to 1, suppose. So then what you have something like 1 by 0 kind of term, which is nothing but, now you have e to the power infinity, right? So then so 1 by e to the power infinity plus 1 would mean 1 by infinity, right? Which is like 0. So there the mean occupation number becomes 0. So based on these two limits, you get two different values. What is this telling you? It is telling you that whenever, as long as your energy is, like your chemical potential is larger than epsilon, or your energy state is lower than mu naught, your mean occupation number is 1. Okay. But otherwise it's all 0, right? So at T tends to 0, or when like at 0 temperature, what happens? This is how your Ne versus energy looks like. So there is a maximum energy till which you have Ne as 1, and below that it becomes 0. So this energy is called the Fermi energy. Okay. It's the energy till which you have your particles there. Okay. So below this, it is all, beyond this, it's 0, meaning there are no particles here. N epsilon is 0, right? So all your particles lie below this energy state called the Fermi state at 0 temperature. Okay. So now if you look at the same expression of N, okay, but in this limit, what would happen? Initially, you had an integration from 0 to infinity because your energy ranged from 0 to infinity. But now your energy ranges from 0 to only the Fermi energy. Okay. And this mean occupation number has essentially become 1 for that limit, right? So here the limit changes from 0 to EF, and the mean occupation number becomes 1. So this changes to a form like this. So you can now get an expression for N versus N to the Fermi energy. Okay. So you can write Fermi energy in terms of the number density, Okay. And also you have this degeneracy term coming in here. So that means if the number density is the most important term, right? So it's telling you that the Fermi energy or the maximum energy till which you have your particles distributed at zero temperature, that goes as n, the number density, to the power 2/3. Okay, it's the number density that governs. Okay, now because you also know the relation between energy and pressure, right? You know the total energy is given as 3/5 NEF, and then you also know for a you know non-relativistic particle, pressure and energy is related by this relation, 2/3 E naught by V, right? So you can again put in that value. So that again gives you this relation between the Fermi energy and the pressure, right? So what is this telling you? You again have a number density involved here, right? So what is the functional dependence of pressure to number density? So your EF, which is the Fermi energy, that goes as n to the power 2/3, and then you have another n here. So that means your thermodynamic pressure now goes as n to the power 5/3. So it's the number density on which the Fermi energy depends, on which the pressure depends, and these are the relations. Okay, that's at the low temperature limit. Okay, at high temperature limit, it tends towards the classical results, and that's what is also expected, right? So that's about Fermi gas. Now, the similar kinds of treatments can also be done for Bose gas. Okay, and there what would change? Basically, now you would have change this term to -1. Okay, your NE values, okay, now will change, right? So all these expressions when you had derived. So if I go back to so this expression basically, so we have been working with this expression, right? So now you have to put -1 here for the uh, Bose-Einstein case, and accordingly all the other terms would change, right? Because for the Bose-Einstein case, this is the relation. From here you get this form of your Q. So in all places where you had A, for the Fermi case, you had put it as +1. Now you have to put it as -1. And then you have to repeat, you can repeat all these expressions, all the analysis that we had done for the Fermi Dirac case, and you would get different results that relate and tells you how things are different between a fermion and a boson, right? So that's, I think, these relations are very important, okay? Okay. So now, based on what we have discussed so far, if you want to answer some questions, okay, the pressure of a non-relativistic free Fermi gas in 3 dimension depends at t equal to 0 on the density of fermions n, as this is something we just discussed, right? So it goes as 5 n to the power 5/3. So the answer would be A, right? Again, consider this case. Consider an ideal Fermi gas in a grand canonical ensemble at constant chemical potential. Okay, the variance of the occupation number of a single particle energy level with mean occupation number n bar is how much? Okay, so basically you are now trying to find the expression for variance. So where do you get the answer from? So this is something we just discussed few slides back, right? We discussed about the statistical fluctuations in n epsilon. So now you basically have this term here. So you have to find variance. So that means you basically have to find this term, only this term here. So you can take this denominator here to the right hand side. So what will you get? You will get average of n epsilon minus a into average of n epsilon squared, right? So now you can take n epsilon average as common, which is nothing but n bar, right? So you would basically, what I'm saying is you want to find this term that is there in the question, right? So that means you have to take this to this side. So what will you get? You would get n bar, which is nothing but average of n epsilon. Okay, this term. Okay, so n bar minus a into n bar square, right? So you can take n bar as common. What will you get? You would get 1 minus 1 minus a n bar. Now, if you're talking about Fermi case, we know that a is plus 1, right? So basically what do you get? You get n bar into 1 minus n bar, right? That's how variance depends on the average number of particles, like the mean occupation, right? So that means you know the answer for this question, which is this, right? This. Clear? For a Fermi, for a Bose-Einstein case, again, your A will change. So this expression would accordingly change, right? Okay. Now again, here you have a question says that if the number density of a free electron gas in 3 dimension is increased 8 times, its Fermi energy will increase or decrease by how much factor? Okay. So that means you have to relate n in 3 dimension. You have to relate n with EF or TF. TF would be proportional to EF, right? So basically you have to use the relation between N and EF, okay? And this is something we have just derived, right? This is the relation. So EF goes with N as N to the power 2/3. So you can basically use this relation and consider the fact that EF is proportional to TF. And from there, you can actually find a relation between the Fermi temperature and the number density. Okay. These are like quite straightforward questions, which directly comes from the relations that we just derived and discussed. Okay, so that's why I spent more time discussing the basic relations and how to get to those relations, because typical questions from this section often just makes use of these concepts. Okay, so once I would always suggest try to at least do these derivations once so that you get used to how they are being done. Okay. So suppose if you are starting from this point here, obviously you can do all of it, but like this exercise by itself. So you start from the summation. So the summation, and then you go to integrations and you do all these integrations, okay? And see how these relations come up and they match with the classical limit. And then under what condition, when you go to low temperatures, how they differ, right? So this exercise, like doing it at least once, is, I think, useful. Okay. So yeah, I guess that's it. If I have to summarize what we discussed today, we started with our very idea of how different energy states. So if you have a quantum system where there are, so first we started with distinguishable and indistinguishable particles and what are the different particles, how, even in indistinguishable case, based on whether you define it by symmetric wave function or antisymmetric wave function. Okay, and then you have distinguishable case. So in all these different kinds of particles, how the number distribution, that is how you distribute these particles in different energy states, how they vary. Okay, first we looked at those distributions and made use of our knowledge of permutation, combination, and probability there. And then we took up individual cases, okay, where we said that now if you know how the distribution is supposed to happen, can you define the number of microstates? And from the definition, from the number of microstates, okay, so from the number of microstates, can you define, so this is also, number of microstates for all the different cases. can you define thermodynamic variables like entropy? Okay, and there you made use of the fact that, okay, the most probable distribution, you know, plays the most important role. So we try to find the most probable distribution, and from there we get these expressions, and then we try to, so this is the most probable value of n for a particular energy state based on different types of particle it changes, and then we put in this value in the expressions for entropy, try to relate different thermodynamic variables to this distributions, okay, how things are distributed, and these are the typical relations. And then what did we do? So once we had these relations based on different particles and different distributions, we now went from like the summation definition to the integration definition, and we tried to find how you can define, actually get expressions that relate the different thermodynamic variables, okay, based on whatever type of particle you choose. We mostly focused on Fermi-Dirac today, okay. We looked at different cases. So these are this like this analysis that we were doing. This gives you the expressions for the different particles and gives us a relation that relates. So this is a very general relation, right? And then you put in all the different conditions. And as you put in the different conditions, different weight factors, you get an expression. So this expression is very important, okay? So you get an expression for particle dependent, this expressions of potential, or very important is the expression for the mean occupation number, okay. And then from there you can define all other terms. So see here, it's nothing but mean occupation number multiplied by the respective energy values, right? So similarly for other thermodynamic variables also you can do a similar relation. So we looked at how the mean occupation number changes for different types of particles, and then included that in our, uh, expressions for pressure and energy and so on. And from there, looked at how the energy dispersions can be included in our calculations to find a relation about between thermodynamic pressure and energy and volume and all of that. We looked at the relativistic particles, non-relativistic particles, okay, which differ in the energy dispersion. We also looked at, for the Fermi-Dirac case, we looked at what happens at low temperatures as well as at high temperatures, okay. Low temperature, it goes towards the quantum limit where you get this very idea of Fermi energy coming up, okay. And we saw that the Fermi energy or the pressure, all of that is related to the number density, okay. And then in the high energy limit, you go to the classical description where your results match with the classical results, right? So that's something we discussed today. So we can build upon this and we can talk about Bose-Einstein particles. We can see how Bose-Einstein condensation happens, okay, at when epsilon tends to mu, like epsilon minus mu tends to 0 in those limits. And then, also the classical cases are, of course, there. So the same concepts that we did for the Fermi-Dirac case can be extended to the other particles, types of particles as well. And we can see how they differ thermodynamically or how they differ statistically. Okay, so how the statistical number distribution differences, okay, actually affect the thermodynamically observable variables for different particles. So yeah, that's all. Thank you. Thank you.